Okay, so let's see how we can actually take a look at vectors and start to manipulate them in some way. All right, so first up, let me just start with a simple example. Suppose I have a vector v, and that equals, let's just say, oh, I don't know, 1, 2. Okay, so graphically, what does that look like? Well, graphically, it would look like this. I would go 1 unit over, and then 2 units up. And that would be where the end of my vector is. And then the vector would look like that. That would be the vector v. Okay, now what if I wanted to sort of elongate it, okay? Well, one way of doing that is by a technique known as scalar multiplication. Now, scalar multiplication is the following. I just take a scalar, and by the way, a scalar is just a fancy way for number versus a vector. So a scalar is just a number like 5, or -2, or a half, or anything. And I multiply a scalar by a vector by doing exactly what you think scalar multiplication would do. And in fact, the exact same thing you do with matrices. You just multiply every component by that. So for example, if I considered now, let's say, 2v, scalar multiplication would just take each component and multiply it by 2. So I'd be now at 2, 4. And what would that look like graphically? Well, graphically, I would now be at 2, 1, 2, and then 1, 2, 3, 4. So graphically, I'd now be right here. And this new vector would be way out here. Look at that. That's a huge vector. Ooh la la! That's a big one. Now, that vector, you'll notice, actually is in the exact same direction, as the original v. So this was original v here. The only thing that's changed is the magnitude. And this is now 2v. So that's the only difference. And you can start to see what's going to happen. If I multiply by a number that's really big, it's going to make the vector really, really long. Ooh la la! But what happens if I multiply something that's sort of small? For example, what if I took half of v? What do you think would happen? It would take this vector and shrink it by half. So now it'd be a little teeny vector. What about negative? What if I were to multiply by a negative number? For example, what about negative 3v? Well, then I'd multiply through by negative 3. I'd see negative 3 comma negative 6. And what would the effect of that be? Well, the effect of that, actually, the negative sign is going to actually flip how the arrow's pointing. So now the arrow's going to go this way. It's going to go this way, and the negative 3 means I go down 3 times the length of this. So in fact, it's going to be off the page. You have to use your imagination because my screen's not big enough here. But it would go all the way down to negative 3 over and negative 6 down. It's in the exact same direction, but now it's 3 times as long, and the negative sign means I flipped over the origin. You see that? So in fact, scalar multiplication just requires you to multiply each of the components through by that scalar. So it's easy to do sort of arithmetically. And the geometric interpretation is also clear. It just elongates or shrinks or flips, if the number's negative, by that scalar. So nothing else changes. Okay, now, one thing we like to do is if we have a couple vectors, we want to put them together and combine them. So what would it mean to add 2 vectors? So let's think about that for a second. Suppose I have 2 vectors. Let's say I've got 1, 3. So that's some vector. And I now want to figure out what it means to add it to another vector, 2, 2. Well, let's think about this graphically first and see sort of what would sort of be a reasonable thing to think about here. So the first one is 1, 3. So 1, 1, 2, 3. So the first vector sort of comes up to there, 1, 3. And the next vector is just 2, 2. So we have 1, 2, comma 2. So the next vector is sort of over here. Notice there's different vectors because they're pointing in different directions, and they potentially have different magnitudes. And I want to ask, what does the sum of those 2 vectors equal? Well, if you think about it sort of analytically, it's pretty easy to add 2 vectors. What you do is just treat them like matrices, basically, and you add the appropriate components together. So I just add the first components together, 1 and 2, and that makes 3. And then I take 3 and 2 and add those together, and I get 5. But what does this mean sort of geometrically? Well, what's actually happening is something really pretty cool. What's actually going on is I take these 2 vectors and I consider them as being adjacent sides of a parallelogram. So if you now put in the rest of the parallelogram, it would look something like this. So now I'm just going to fill in the rest of the parallelogram. See, parallelogram, all I did was sort of take this thing and sort of copied it up here, took this thing, copied it up there. So now it's a parallelogram. These are two sides. It turns out that this vertex right there is going to represent the end of the sum of those two vectors. Isn't that cool? So it's way out there. And if you look, even visually, this looks pretty good, because if you look, that point seems to be at 3. 1, 2, 3, 4, 5. I mean, visually, it even looks really good. So adding vectors, in fact, is no big deal. You just take the two vectors, and graphically what you do is you just consider the parallelogram that they form, and then you look at that far vertex, and that tells it to you. So, for example, let me just take a look at another problem here. Well, in fact, let's just do another one on another page. So that's the answer. Subtraction works the exact same way. You have 3, 2, and you want to subtract 1, 4. Well, what you do is you just subtract. 3 minus 1 would be 2. 2 minus 4 would be negative 2. And what would that look like? Well, subtracting, just sort of adding in reverse. So you're sort of doing a reverse process here. So what does this look like? You have 3, 2. So let's put in 3, 2. So 1, 2, 3, 1, 2. So you've got one vector right up there. That's that first vector, 3, 2. And now I want to subtract this vector, which is 1, 4. And so 1, 4, 1, 1, 2, 3, 4. It's way up here. And I want to subtract that vector. Since I'm subtracting, geometrically, what's going on? Well, if you think of subtraction as just adding a negative, if I think of this as 3, 2 plus negative this, then I can use the adding method. So let's do that. So let's look at negative 1, 4. So what would negative 1, 4 be? Well, that would be negative 1, negative 4. Just taking negative 1 times that vector. It's a scalar multiplication. And what do I see? I see negative 1 and then negative 4. It's way down here. It's all by itself. The lonely shepherd right here. That's sad. It's all by itself. The lonely shepherd vector. Now, that vector represents negative 1, negative 4. So now to combine this, all I've got to do is add these two things. So if I add these two things now, what do? Well, I make the parallelogram. So this is always a little tricky here. 1, 2, 3, 1, 2. So if you make the parallelogram carefully, it should look like this. And now I'll make it a little darker so you people on the information superhighway can see it. Okay? So this is actually, if I call this vector W and this vector V, this vector here is negative V, because that's what I'm doing. I'm taking W plus negative V, and this is W. And then the answer, the resultant vector, would be this one right here. And what is that? Well, notice it is 1, 2, negative 2. So in fact, you subtract vectors by subtracting components, and visually, if you want to visualize it, if you take the two vectors, you take the second one, the one you're subtracting, look at its negative, and then add its negative to the vector, and that gives you this. Anyway, you can see now how to add and subtract vectors together. It's sort of this parallelogram business, and just component-wise combining. And scalar multiplication, you multiply everything through by scalar. It either elongates, ooh la la, or shrinks. If you want to add vectors, you just add up the components, make a parallelogram fine. If you want to subtract vectors, you take the one you're subtracting and look at the negative of that. So it's all by itself. It's the lonely shepherd. And then you do the little parallelogram adding business. Okay, up next we'll take a look at some more both visual and algebraic issues involving vectors. I'll see you there.